Good afternoon and welcome to the CERIAS Security Seminar from Purdue University. Our presenter today is Brendan Saltaformaggio. Brendan is a doctoral student in computer science here at Purdue. And the project that he will be talking about today most recently won the Best Student Paper Award at the 2014 Usenet Security Conference. Brendan?
Thanks. Okay, so today I'm going to talk about a project that me and Zhenshu Gu, who's in the audience, and my two advisors, Professor Shenyu Zhang and Professor Dongyan Xu, have been working on. The title of the project is DSCRETE. It's about automatically rendering evidence out of memory images for use in digital forensics. So Joel just announced one of my accolades. This did recently win Best Student Paper Award, but more importantly than that, the CS department posted this on their Facebook and it got 15 likes. It's the highest number in recorded history. Okay, so I'm going to start off this presentation with a story. And it's based on some true events that happened here at Purdue University. If I can find my mouse. There we go. So some of you may remember actually when the email went out about a student who was changing grades. So let's imagine that we're watching this cybercrime go on in real time. Student here is changing grades on an official university grade report. And he's doing this for both himself and some of his friends and accomplices who may have even paid him for this service. But notice, before he can save this document, he's still in the process of editing it, law enforcement agents arrive. Bad for him. They seize that computer, they image its memory, and they return all of this to the forensics lab to perform their investigation. And I'm going to show how DSCRETE will be used to analyze that memory image and recover that PDF that's frozen in the computer's memory. And so note that recovering this PDF is essential for this investigation, because without that PDF that he was in the process of editing, the police have no connection to the accomplices that are in this crime. So obviously we're talking about memory forensics. Memory forensics here, we want to recover the live evidence that's currently being processed by the computer in its memory image. So like I said, those PDF edits that we want are only in the computer's memory. Disk forensics in this case will do you no good. But then this brings up the question, how are we going to recover exactly this evidence that's in the memory image? Because remember, a memory image is just a blob of raw binary data. We've got to chew that up somehow and come up with evidence from it. And further, we don't even know what a PDF looks like when it's in memory. It could look like anything. It could look like whatever the application was editing at that time that's now frozen in that memory image. And so the key idea behind memory forensics is that we want to find the application's data structures, the formatted, understandable data that it was in the process of manipulating when this memory image was taken. So the state of the art dates back a little bit, but it started out with some value invariant based signatures. So what that means is you have a data structure, and you know that there are patterns of constants and predictable fields within that data structure, and so you build a signature based on that. And then you just brute force scan through that memory image and you try to recover these data structure instances. So of course, this was initially proposed at a very big time level by a guy named Brendan Dolan Gavitt. This was in CCS quite a few years back. And they said that you could perform dynamic analysis on a Linux kernel, and you could watch how that Linux kernel touched memory, and using those signatures, you could generate these data structure, you could figure out the commonly used fields within the Linux kernel's data structures. And so you could use those signatures to then scan memory images for these kernel data structures. And then later on, other papers did the same thing with recovering data structure signatures from user mode applications in different contexts. But the problem with these is that value invariant signatures are very brittle. They rely on you just knowing, oh, this field has to be a constant. Oh, this field can only be between 10 and 20. So you can see that that can easily break in practice, and it's easy for an attacker to break this as well, right? You can just fiddle with those important fields and no longer can your data structure be found during an investigation. So to kind of beef up this idea, people figured out, well, data structures naturally form networks in memory. And so if we rely on this network, on this connectivity of data structures within a memory image, we can just find one and then naturally walk the pointers out to find all the data structures we're interested in. So a paper that really introduced this idea, published by my advisor and some previous PhD students of his, SIGGRAPH, says that you can look at the source code of an application, and that will tell you the points to relationships between the data structures, and then using those you build these signatures, these network signatures of how the data structures interconnect. But the problem is that you have to assume that data structures here are highly connected. If a data structure doesn't point to anything, there's no way you can get it using this approach. And also, this requires source code in this paper, and other papers have tried to do it without source code, but it turns out to be very difficult because at runtime, you lose the concreteness that source code gives you about this points to relationship. So, let's hold on a minute. That was the state of the art before discrete. We were finding these data structures in a memory image and returning them to an investigator. So believe it or not, this is that PDF that the suspect was just editing. It's in raw data structure form. You can see the problem. No matter how good the state of the art is at uncovering these data structure instances, you still can't figure out what this PDF says. It's still just a blob of data to you. And this happens for all kinds of types of data structures, like passwords, images, formatted or encoded data that's in memory. Actually understanding the content of these data structures is extremely difficult, if not impossible, for human investigators. So we want to address this problem. We're calling this the content reverse engineering challenge in memory forensics, actually understanding the content of these data structures. And so we make an observation in this work. An application, when it defines a data structure, like that PDF we were just looking at, it also defines some printing or rendering logic for that data structure. Let's call this the P function inside of an application. The P function should take as input that raw in-memory data structure instance, chew it up, format it, do some kind of processing, and then output it to some kind of human understandable output, like a PDF file. So for a running example, let's assume we have this source code for that PDF editor application. You can see that the first line defines this PDF data structure. We're going to load a PDF file in from disk, and that's going to allocate and initialize these in-memory data structures. The main loop allows the user to make his edits to the PDF. And then the save PDF file function is invoked in order to take that in-memory data structure, process it, format it, and output it to a PDF file. And you can note that we've illustrated the P function here inside of this application as that save PDF file function. It does just what we said. Discrete aims to reuse this P function to build what we call a memory scanner plus renderer tool. The intuition here is that that P function is going to perform in-depth processing and formatting of its input. So when you present P with invalid input, you can assume it's going to crash. Based on this intuition, we want to present every offset in a memory image to the P function. Eventually, we're going to hit that data structure instance that's frozen in the memory image. And for that, P is going to render the natural application output that would have been generated by that application with its data frozen in the memory image. So to build a scanner plus renderer tool, the lab forensic staff has to recover the target binary that they're interested in from the suspect's computer. And so this can usually be done with disk forensics because you'll get an image of the hard drive. You just pull that binary off. And then they're going to use DSCRETE in two dynamic analysis steps to build a scanner plus renderer tool. And then that scanner plus renderer tool can be reused in all the future investigations of that same app. So it's an application-specific scanner plus renderer tool. So let's look exactly how those two steps work. The first step, we want to find that P function within the application. So the investigators are going to execute that binary that they've recovered from the suspect's machine. Then we're going to use slicing techniques in order to find the entire printing and output component within that binary. And during this, the investigator is just going to select the output functions that they saw rendering that evidence that they're interested in. So for instance, it's going to be the fwrite function call that actually saved that PDF file we're interested in. And then meanwhile, in the background, DSCRETE is going to be saving snapshots of that application as it's running to be used in step 2. So now in step 2, once we've isolated that whole output component in the application, we're going to want to find the entry point to that P function. Here we define the entry point as an instruction within that larger output component that takes as input a pointer to some data in the heap. And then all of the future output functions that the investigator selected have to be dependent on that entry point. So the idea here is that by changing the data structure pointer handled at P's entry point, we can change the output produced later on down by the P function. So to do this, DSCRETE is going to look at that program slice and it's going to identify a number of candidates for the entry point. And then it's going to test these candidates in a process that we call cross-state execution. So to do this, the investigator is going to execute that binary one more time, and in the background, DSCRETE is going to test each one of these entry point candidates. So I'm going to show exactly how cross-state execution works right now. So imagine again our PDF editor's code. Notice that DSCRETE has already marked that invocation to the save PDF file function as the candidate. So we start executing this program, and it reads in that PDF file from disk. It's going to allocate and initialize the PDF data structure, and so you can see that it's using that data structure in its memory. The main loop is going to execute. The investigator is going to make some simple edit to it, and it's going to continue to use those PDF data structures in its memory. But then we're going to hit that identified candidate. This is where DSCRETE is going to begin the process of cross-state execution. To do this, it's going to perform two quick steps. First, it's going to map that memory image that we took in step 1 into the new process's memory space. Then, it's going to switch that myPDF pointer that the application is using to point to the old data structures that are frozen in that step 1 memory image. And so you can see that this is going to cause the remainder of the execution to happen using the old data structures that are frozen in that step 1 memory snapshot. So a key observation here is that a correct entry point candidate will reproduce the output we saw in step 1 of running this application. So it's also important to note here that the application input you use in step 2 must differ from the input you use in step 1. If not, you'll get the same output in both cases, and you won't be able to tell which one it came from. So once you've identified that correct entry point candidate, DSCRETE's just going to package up that logic into a scanner plus renderer tool. And the scanner plus renderer tool works in the same way, using cross-state execution. You're going to feed in a suspect's memory image, and it's going to present each offset in that memory image to the P function. Using cross-state execution, eventually it will hit the real data structure that's in that memory snapshot and naturally output the evidence. And again, this tool can now be distributed to various field investigators or things like that to be reused in all future investigations of this app. So let's return to that crime story. So back at the forensics lab, let's start. There we go. So back at the forensics lab, DSCRETE's going to be used to build one of those scanner plus renderer tools. So first, like in step 1, we're going to execute that binary that we've taken from the suspect's computer, and we're just going to give it some simple lab test PDF. The investigator is going to make a simple modification and save the file. In the background, DSCRETE will be tracing the execution and recording those I/O functions and saving the memory snapshots to be used in step 2. Now we just want to go ahead and mark the output functions, which DSCRETE found outputting that evidence. And so just a quick scan through the log, and we see that all of these fwrite invocations saved that PDF file that we were just editing. So we'll leave all of these marked for DSCRETE. Now we're going to start step 2. We just execute the binary again. And this time, in the background, DSCRETE is going to be using cross-state execution to test those entry point candidates. You may not be able to see it. It's going to fly by on the terminal. But DSCRETE identifies, in this case, 46 entry point candidates. Notice we never actually have to see any of these entry point candidates, but they're going to be tested automatically in the background. So here we go. Investigator opens a different test PDF in this step. He's just going to make some different simple modifications, and in the background, DSCRETE is testing those entry point candidates. Now that that's done, we're going to review which of those candidates produced any output. So of the 46 candidates, only 6 actually produced any output. Candidate 1 is wrong because it produced the step 1 PDF. Candidates 2 and 3 are wrong, they just produced garbage. But then we find that the last 3 candidates, all produced the PDF from step 1 that we were interested in. So DSCRETE is going to take one of these correct candidates and package it into a scanner plus renderer tool. And now we're going to use that scanner plus renderer tool to catch that criminal. So we're going to run the scanner plus renderer tool with the memory image taken from the suspect's computer where he was editing that PDF. And this prototype of DSCRETE just requires us to execute the binary again just to get it to that entry point for the P logic. At that point, DSCRETE is going to take over and begin the memory image scanning. So the scan begins, and then about 30 minutes later, we get our results. So we can go check the results that were produced from scanning that memory image. And sure enough, as we expect, only one PDF is generated. And it is indeed the PDF with the higher grades on it that show not only the crime, but also the accomplices that were involved. And so, as a reminder, without DSCRETE, even the best we can do is just recovering these raw data structure instances from that memory image. So we didn't just test DSCRETE with PDFs. We tested a variety of different digital evidence, all which require some form of content reverse engineering in order to understand. We had things like images, snapshot images from the GNOME screenshot application, which is the default screenshot app for most Linux distributions, Nginx web servers, request log, as well as PDFs like we saw here, process data being rendered by the top application, even vector graphics drawn in the XFIG application, and then a bunch of others that you can see on the chart. And as you can see, in most cases, in almost all cases, DSCRETE is perfectly accurate. No false positives, no false negatives. That's because the rendering logic itself contains all of those invariants about the data structure, the points to invariants, the constant data invariants that would have to be reverse engineered by the other techniques. They're encapsulated in that printing function, and so here they naturally cause discrete to find those data structures. If you're interested anymore in the negative results, we can talk offline about it. And if you're curious about the performance of these discrete scanners, the one we showed today took about 30 minutes. They're all about that window, which is perfectly fine for a digital forensics investigation of this scale. And so, in conclusion, in the paper and in this talk, we've identified that the content reverse engineering challenge that exists in memory forensics. And based on that challenge, we've designed DSCRETE to leverage binary reuse to both locate data structures in a memory image and then automatically render them as evidence. And our evaluation shows DSCRETE to be highly effective at doing this. And finally, DSCRETE and content reverse engineering is still in its infancy. This paper pretty much introduced it. So there's still lots of opportunity for our work and future work to address other challenges in content reverse engineering. And so with that, I thank you all for listening, and I'm open to take any questions you have. Yeah.
My question is about the binary that you use for analysis.
Mm-hmm.
Do you need an authoritative binary or an application that is widely used, or can you theoretically do this with something that they wrote on their computer?
Yeah, you can use any binary in this. I mean, the only assumption we make about the binary is that it runs on PIN, which is a binary analysis platform. But Intel says that's anything that runs on Intel. So, yeah, we at least I've never seen anything that didn't run on PIN.
Okay, thank you.
Sure.
So is DSCRETE then robust when operating against packed or self-decrypting binaries also?
Yeah, since it's re-executing the binary in place, it naturally handles that stuff. So if it's packed, it'll just unpack itself and execute. And DSCRETE will identify that P function wherever it is within the binary. Any other questions? Okay, that's all I have. Thank you all very much.